Hello, everybody. My name is Thomas Wild, and today I'll be presenting my master's thesis entitled A Practical Investigation into Potential Improvements for Testicular Shielding and Abdominal Radiotherapy. This has been in association with UWA and Charlie's, and my supervisor is Pejman Rashan Fazet.
Now, should we go to the next one? I've been moving.
There we go. Alrighty, for this presentation, we'll just quickly cover my introduction and the motivation for this project, the methods and materials used for it, my results of the project, the discussion of these results, and a conclusion and ideas for future research. So, before moving on to granite shielding, I feel like it's prudent to mention the anatomy of the testicles. So the testicles are an external organ and the site for sperm production in the male. So this site exists at the seminiferous tubules with these coiled subunits there within the testicles, which are directly adjacent to the Leydig cells, which are responsible for testosterone production. And all that is important to keep in mind. And also when sperm is produced in the seminiferous tubules, it starts off very radio sensitive and then it gets harder and harder as it develops. Crucially, it remains in the testicle until the point of ejaculation, at which point then it leaves by the vas deferens, meaning that if we are considering the issue of sperm production, we only really need to consider the testicles and no other organ. And so I feel like now we should turn to what happens when you irradiate the testicles. So 4 things are known to occur. That is testicular cancer. And now this is not more particularly relevant than any other type of cancer when radiation exposed. Testicular cancer has a high survivability rate of 97%, and it's not particularly more likely to occur than any other organ. The second issue is inheritable mutations, which is unique. That risk is about 0.1% per sievert, so it's prudent to mention, but not the main focus. Thirdly is, of course, damage to the testosterone production. So after known lower abdominal radiotherapy procedures, you can see a reduction in testosterone production up to about 80% after a 6-month period, and that can have long-term endocrinal issues. And finally, and the one most prudent to this discussion, is sterility. So if the testicles are exposed to more than 0.1 gray, we can see temporary or just general altered sperm production, which can be quite inconvenient. And for more than 1 gray, we can see likely chances of permanent sterility. So that's kind of our ballpark area of what we want to avoid. And if you go over 5 grays, you're looking at definite permanent sterility. And this can have long-term psychological and economic impacts on families and the idea of masculinity itself. And so there are lots of lower abdominal radiotherapy procedures where we approach this risk factor. That's the bladder, the prostate, the rectum, all kind of lower abdominal therapies like that, lower lymph nodes as well. And we are looking at about anywhere between 0.06 gray to 6.48 gray as kind of the ballpark area for those procedures. And so we are hitting altered sperm production, permanent sterility, and temporary sterility there. So it's a cause for concern. So we can alleviate this. That would be very good for people's quality of life. And so we can reduce this with radiation shielding. So basically, the idea is just to reduce the dosage through a highly attenuating material. Good candidates for this typically have a low half-value layer and a high linear attenuation coefficient, which are therefore associated with high densities and Z values. Most papers on gonad shielding generally use lead and cero bend, but these are both very problematic because lead involves a very high working temperature, so it's inefficient, not very economical, and can be expensive to get custom components. And cerebend has very high cadmium content, so it's incredibly toxic. And other low melting point alloys that I often use often contain things like indium, which can give you indium lung, which is also incredibly toxic, despite having a low melting point, which is incredibly preferable for manufacturing procedures. So I proposed the alternative of LW7, which has a very low melting point and is bismuth based. And because it's bismuth, it has incredibly high spatial resolution when you make things with it, because bismuth, like water, expands when it cools. And it has very low melting points, which is incredibly good for manufacturing. It has very similar attenuation properties over 4 to 18 with Safe, which is another candidate that's often used, and it's made of tin, lead, and majority bismuth. And it's much safer as well to work with. So it leads me to the aims. There's 4 of them. So firstly, the aim of this project is to design a testicular shield based upon what we know about it, and then construct it physically as an exercise in the ease of use of the material, as an economic analysis, just to kind of get a feel for what it would actually be like in the real setting. Secondly, to construct a simulated person, as in the phantom, that we can test it on as close to a geometric human being as possible, as cheaply as possible, and then to measure the dosage. And then finally, after doing that in a normal abdominal pelvic procedure, we would then assess both quantitatively and qualitatively the suitability of it, whether or not it should be recommended or not. Alrighty, so I'll just explain quickly how I built the shield. So the 2 methods we utilized, the silicon method and the ABS method, both to kind of gauge a method of how you would do this in a clinical setting. So firstly, I designed on fusion a simple box method. This is silicon, I should point out, with a bunch of different components, just simple PLA. And then the idea then was to grab the silicon. This is high temperature resistant silicon, which is why it's good, because you need something that won't bust after you get over that 96-degree threshold. PLA will get gooey and melt if you do that. So yeah, if you pour the silicon in and around it, it gets really stuck to things. So you can't just put the PLA shield in, pour around it, it'll get fused. You have to kind of do it in slow bits, where you do this and then glue it to that and glue it to that. So that's kind of the idea of sticking it all together. And then when you pour it, you put it on a vibration table. The vibration gets all the air bubbles out, and then you're left with that. And then you just simply squeeze it out. So that's what we got for the silicon shield. You can see it's pretty dodgy. The spatial resolution is quite poor, but it was fairly easy, a little time consuming. And that leads me to the second method, which was the ABS method. So we put it into several different components. ABS has really good temperature resistance for this, so it won't melt when you pour the metal in. So then again, the metal was poured in, strapped down, and the vibration table was used, and you can see the results significantly better. The only markings at all just there where a screwdriver was used to yank it out. Of course, the ABS itself was completely destroyed after use, so that is one difference. You can do this again and again and again, whereas this one's kind of one and done, but it's cheaper in the long run because you can manufacture loads of different ones, and all it takes is a slightly different fusion design. All right, so now I'll touch on the phantom design. So that's what it looks like in fusion. You can see that's kind of what it would look like when it's done without the testicular inserts. It's designed to have testicular insert put in for measuring purposes. So it was printed at 3% infill at a PLA with thick size 10 layer walls and ceiling and size 5 walls. The reason this was done is because we were going to use gelatin. So the gelatin was poured at 11% weight by weight with 89% vinegar water mixture, the vinegar being used to stop the rot of the gelatin to make it last a long time. And this has shown very good effectiveness to replicate human tissue at a very basic level. And the gyro therefore hold it all together, because with gyro you can kind of pour it in and it takes up the whole area without overflowing or going into it. So it gives it quite a firm thing to grasp upon, and there's good precedent for it in the literature. So yeah, it's quite good for that reason. So we basically just poured it into all the different sections, just drilling a hole into it. And the way I did it, it hardens with actually when air hits it, so you don't need to rock it up with anything. And so this is the final result. So you can see that's the disassembled components. There's 8 pieces there, and that's what it looks like laying down when you would put it in a supine position for treatment. And so these are the 2 different what I call gonad inserts which go in there, which are the actual size of the testicles. So you can see it's a very geometric model, basic, to alleviate other problems, which I'll touch on in the discussion. You can see here, this is for the film cartridge. So that's the dosimeter that we're going to use there. And this is for an ion chamber, which explains why there's a hole in the shield, which you may have noticed earlier, just to get the ion chamber in. So yeah, we can put it in there, test with the ion chamber, take it out, put that one in. So it's very customizable, very easy to use, and very easy to disassemble. So you can put film all the way through it to test for whatever you want. And therefore I'll go to the experimental procedure. So you can see we cut out some film with these different sizes. That's for the thigh, that's for the surface dose of the testicles, that's for the PTV, and those little ones are for inside the testicle. That's really the important one. The rest will mostly just have interest. And so you can see here the treatment plan. So we CT stand it next to Gabor. We're going to do that. And you can see this is with the shield and that's without the shield. So you can see it's kind of pushing far from the edge of the field. And so treatment planning system we were able to estimate the doses from, and we were able to perform gamma analysis later. And you can see here that's what it looked like when it went into the neck. Thanks to Machine as well for the treatment planning, and for Machine and Linear for the neck stuff. So yeah, you can see that's what it looked like in there with the ion chamber in there. That's without the shield while we were lining it up. So you can see it was supine, ready to receive the treatment. Our treatment was done at VMAT 30-30 for MLCs, and it was done in 2 fields at 6 MeV, and then the target dose for PTV was 2 gram at an SSD of 90. All right, so with that, I'll lead now to the results. So you can see here on the left, we've got the results for the HU value for the body. On the right, the HU values for the gonads. So on the left here, we can see the target value was 30. That equates to kind of what we'd expect in between 20 and 40 for that kind of area of that tissue. Again, I said 3% infill with 11% weight by weight gelatin. So if you on Slicer go and take a segment and exclude your air gaps, we were looking at from the CT scan median at 19 and median of 22, which is a little lower than we expected. And by taking a confidence interval based on what we got, we can see that there is likely a systemic issue as to why it's a little lower than expected, which I'll touch on later because I think I know why. And on the right here with the gonads, the target was HU, that was taken from a CT scan of the same person's gonads. You can see that it was a little higher than expected, and we have systematic reason to think that might be true. And I think I know why that is as well. And that was done with 95% infill PLA, based off the work of Ashleisha and the determination of HU versus infill values of standard PLA. Alrighty, so now I'll touch on the ion chamber measurements. This was after the treatment was performed. So you can see on the left, that's with the shield, and on the right, that's without the shield. So with the shield, you're looking at a dose of 0.696, and the treatment planning system expected it to be 0.69. So you can see it's very, very close. So that's interesting to note. I'll mention that a bit later. And on the right, you can see the dose without the shield was 0.754. So you can see a slight reduction there. And on the TVS, we estimated 0.734, which is a reduction of 2.7%. So you can see that the treatment planning system estimated it fairly well, interestingly, otherwise very consistent. So that leads me to the general dose comparison. So with the shield, you're looking at 0.696, and without the shield, you're looking at 0.754, which is a reduction of about 7.7% or 8%, which is a shielding factor of 1.83. And I'll show whether that's good or bad later in the discussion section and compare it to the literature. And the shielding factor, by the way, for those who don't know, is just the dose without the shield divided by the dose with the shield. All right, so then with the film, we had to calibrate it. The ion chamber, and it was just done with 11 pieces of film, 10 with doses, 1 as a baseline. This was manufactured using Film Wizards, so I have to thank Tom and Kaylee for that. And it was done again with similar conditions and above and below 10 centimeters of solid water to produce backscatter and make sure we get the Dmax. Alrighty, so this is the film measurements we got. This is for the internal bit. That's the one inside the film cartridge that sits right on top. You can see there's pretty good agreement generally with the case without the shield. You get a factor of 91.6, which is lower than the target 95 in Australia, but not negligible. So you can see it's pretty similar, and the maximum value ascertained was 0.6 gray. And in the case with the shield, 0.56 gray, which is a small reduction similar to what we saw with the ion chamber, about 6.7%, I believe. And gamma factor is slightly lower, quite a lot lower, sorry, 21.3%. So I believe I know why that is as well. I'll point that out in the discussion section. You can see a fairly standard dose profile, and obviously the difference there in the curviness is just due to the film and the resolution noise. So for interest here as well, we can see the PQV and for the thigh pieces, that's where they were placed inside of the phantom, hence compartmentalization. We can see that dose profile, we kind of under the TPS underestimated what the film measured, which is interesting. And then again with the thigh, we can see it's very high at the top and then dips down quite a bit. I reason that mostly due to the position of where it was done. That's just where the scan is notifying that it was put in an Epson scanner after it was analyzed results. The way it's just picking up the red, and then it drops down here and it's noticing the edge. And you can kind of not really analyze this very well because it's kind of the edge of the film and the crystals could be cut by the laser cutter. And then it's down drastically. And if you look, this is relative and those absolute, by the way. And if you look there, the reason that I believe that it's quite not really picking up well is because it's gone below the threshold value for the resolution of the threshold value for the film, because it shouldn't be able to detect anything reliably below 0.2 gray. So I believe that's why you're getting kind of funky results below that value. But it's good to note that for this kind of procedure, you're not getting sizable doses in the thigh anyway, which is quite a comfort, I believe, to therapists. Alrighty, so for the evaluation, the Phantom overall I considered a pretty good success. It was very good overall. So the actual discrepancies I mentioned earlier. The first one, the difference with the gelatin bit, I believe that's mostly because of the different blooming techniques used by myself and Rachel Williams, whose data I based the HU calculations on, because I believe I made mine a little bit firmer than hers. I didn't want it to leak everywhere, and it seemed to do the trick in not leaking, but you can see there's a slight HU difference. So it'd be good if we did another analysis with that to make sure we got that perfect. And for the TLA, I believe that's mostly just due to the difference in printer done between Ashley's study and my own, because I used a bamboo and she used a Prusa i3. And there's a difference in novel size, to internal temperature, things like that, which can lead to small discrepancies, which could easily be fixed. So yeah, as well, the difference, there was a minimization in air gaps as well. There was, on the CT, you could see there was some small air gaps there, but that was kind of alleviated by using a vibration table as reported. And also when we tilted it after pouring it, it allowed it to seize up at the end, which meant that it wasn't, we were able to fill the whole thing up with everything outside. But still, there are still air gaps because you can't ever be perfect with these things. And the basic geometry is worth pointing out. You can see that it's not based off a CT scan. It's very simply just a person's waist and then an external organ right above it. And there's a few reasons for that. I mean, if you want to do a CT one of this size, it involves using a larger bed, which can take time, be more complex. There's a narrowing of focus, it's more fragile, it's easy to get deformations. If you use gelatin, it could be moving it around, and you have to make a choice between, well, maybe we shouldn't use the gyroid, maybe we should do different infills and things like that. And because that wasn't a major focus of the project, a simple geometric design was used. And also it's quite hard to find CT scans of men that have the testicles external, not attached to the thigh or anything like that, a reasonable size, easy to take like that. So this was just overall a lot easier. Yeah, and there was no leakage at all, which is quite good. So I think that this kind of gelatin style is quite a good idea, generally speaking. And then I believe it's because the gyroid infilled thicker walls, a thicker floor and ceiling, and the gelatin was quite firm. And it was significantly more cost effective than conventional kind of Phantom that you might get. Because some Phantoms can go for upwards of $30,000, which just costs $150, and 77 of that was gelatin. And if you were instead kind of make this shield out of PLA, you're looking at about $400, which I'll show on page. And it's very easy to use, very easy to carry and test with, because you can just break it all the way down, put it all the way back together again, you can put film all over it. Yeah, that's kind of a cost analysis. I won't go too deep into it, but you can see that printing out of 3%, you're getting $52.50 cost and $415 if you were to hypothetically do the whole thing at 95% infill. So you're looking at a much, much cheaper alternative. And it'll last 6 weeks if you do the vinegar at 89% infill. But I'm going to experiment with pouring hot water in it to kind of liquefy and then pour it out, which means theoretically you could do it again and again and again, only having to repeat the $77 cost, which means it could be very cost effective in the long run as well, but I have to try that. Okay, so for the TPS, for the case without shield, TPS measures condition of 2.7%, case with 0.9%. So that's exceptional, because we the ICIU was looking for about 5%, and it was really good, you're looking at 3%, and we've kind of beaten that 3% accuracy. So radiation therapists, when they're looking at the testicles, I suppose, it's kind of a good reason to kind of trust it a little bit and go with that kind of low dose scatter estimation isn't that bad. This is done again with Eclipse version 18. So it's not a bad point to mention at all. And that was the iron chamber. For the film, there was general reduction in gamma value across the cases with the shield and without the shield, as I kind of alluded to earlier. And that's very interesting, because you can see here with the case with the shield, where it's very prevalent, you can see a massive reduction, and with the PTV, looking at a little reduction, with the thigh almost nothing. And I think I know what it is. When we did the Eclipse TPS, there was no like inbuilt LW7 thing for when we put in the shield, obviously because it's so uncommon. So we had to use steel, and I believe the HU value of LW7 is closer to lead because it's high lead content. So you think you'd be looking close to 30,000, whereas steel was about 5,000 less than that. So there was a decrease in accuracy because of that reason. And it's most prominent exactly where the shield is, in value, where you're looking at massive reduction. You see a mild reduction in PTV because you wouldn't expect it be at all, and that's probably the realms of possibility. And almost nothing in the thigh, but that's again because the dose is so low, the film is not able to accurately record it. Yeah. There's also a slightly large air gap in the film size because in order to put the film in, you need the cartridge, and so there's a slight air gap. If you didn't have that, the film would be damaged. High sensitivity for that reason. So let's evaluate the shield now. So for the 6 MeV beam with 2 grey, the 2 centimetre thick shield reduced by about 7%, 6%, 8%, somewhere around there. And if we compare that to the literature, we can see that's a little lower than expected. So generally they'll hover between 2 and 5, but most shielding studies for the guys often use a lot higher energy levels and high doses. So you can see that there's a massive difference in this study which used 6 and the high dose which is that. The choice to use 6 was mostly because it's a smaller body with low fat content, kind of a prepubescent kind of male, whereas some of these were done on adults as well, so you can see a high energy. So if we were to do this test on higher energy, to be curious to see whether the shielding factor would go up quite a bit, because as it stands, the energy reduction is only quite mild, or at least less than I would have hoped. But it's significantly cost effective. The whole thing costs $150, and that's assuming you use a whole roll of filament, when in reality you're going to use barely any. And the great thing is that you can pour the metal into it, and then after you're done with it, you can use it again and again and again and again, and make all sorts of different things. It's incredibly reusable. It has still a 0.1 Pro. So I think you can make something like 200 something shields using one roll of ABS. So it's quite cost effective for that reason. It can be shown to be even more effective. All right, so I'll touch on future research as well. So I'd be curious to see this with TLDs using in vivo dosimetry, and on a CT-based fan to get like a more kind of case-specific example to see if it would work in a clinical setting to a greater extent. And that way we could also use a sealed shield that didn't let any dose in over the top. As well, I'd like to see, as I mentioned, high energy and high dosages to observe changes in shielding factor to see if in other cases it would be more effective. I'd like to compare it to lead bank at baseline because if you can compare it to lead and what's often used like that, it'd be curious to see how much of a change is and whether or not it would be preferable to patients. And I'd like to take advantage of the ABS method to make some other kinds of shields. So in the early stages, I had like 1,000 different designs for shields, and effectively the one I ended up choosing was one that was quite basic because the silicon method, because of the slow spatial resolution, you can't get too many complex shapes. But now the ABS method is generally just better anyway. I'd like to try some funkier shapes and maybe slope up, kind of do thicker on the top, thinner on the sides, things like that, to kind of see if we can pump that shielding factor up a little more. Yeah, I'd also really like if we could test the HU values of some low melting point alloys as well. As mentioned, we had to use steel, which is kind of not really what we would want. Yeah, if we can actually test the HU values of LW7, Rhodes metal, Ceraden, Cerasafe, all these other metals like that, and if we could somehow evolve them into clips, that'd be really useful. I understand this would be very difficult because of the metal artifacts that occur when you put anything metal into a CTCI. But that's why I thought it was interesting to mention, because if someone could solve that, that would be very interesting. And I've seen some papers that have done a good attempt. All right. So I'd just like to acknowledge everyone that helped. So thank you very much, Benjamin Sheed, Mania Gabor, and everyone else, Judge Charlies. They're all incredibly helpful. And all the current student body, I couldn't have done without any of these people. I was really, really thankful. So thank you, everyone. Yeah. Alrighty, thank you for listening to my talk.
Thanks very much, Tom. Appreciate that. Any questions from the room?
Yes, one question from me.
Okay.
Nice talk, Tom.
Thank you.
Excellent work. I have just a question with regarding the phantom measurement. So you said you use the ion chamber and you use film for your measurement. Can you tell me what's the advantage of using film over ion chamber?
Sure. So film gives you a 2D dose distribution. So you can kind of get more of a profile and more of an accurate kind of spread of results, whereas ion chamber is just point-like. And ion chamber is great because it's reliable. It gives you instant readout, which is very much appreciated. Yeah, film's great for that 2D thing, and you can kind of put up long dosing so you can see exactly how it went about. Yeah, it's pretty good overall for that reason, and just gave us a different amount of results. And we could also compare it to the TPS more effectively with the gamma factor. So yeah, that's why.
Do you think if you have to measure high dose gradient, film will be more suitable than ion chamber?
It's calibrated right, I suppose so.
Okay, thanks.
Roger? Might be muted. That's all right. I actually have a question, so I'll jump in. So my question is just in regards to your shielding factor that you calculated. How robust do you think that is? Because as far as I can tell, it's based on 2 measurements.
Yeah, so it'd be excellent if we could do more measurements, obviously, to get a greater spread of data. When you say robust, sorry, do you mean accurate or do you mean relevant?
Yeah, I mean, if it's based on 2 measurements, yeah, how accurate do you think that's about?
Oh, I mean, yeah, I mean, it's a good point to mention. I should say as well, that those values, so we took 2 measurements for the ion chamber case and then averaged them specifically. And then for the film, I should mention that we took 3 with and 3 without. So a little more, perhaps I should have mentioned that we did a little bit more of that. Yeah, I mean, ideally, I'd love to do more and more and more tests, but obviously it takes hospital resources every time to do that.
Sure.
But yeah, I'd absolutely love to do more tests.
Yeah. And I guess, yeah. Please unmuted. Go for it, Roger.
Tom,
Yes.
very nice talk and beautifully logically constructed. Can you go back to slide 14, please? And I probably just missed this.
Yes.
Yes, that's one. The right-hand side. Look, can you just, perhaps only for my benefit, can you just very briefly describe why there's such a discrepancy between film and TPS in the dose profile?
Sure. So the TPS, I was expecting there to be a little something of the phantom here, and then it crosses here into the surface dose of the thigh bit. Yes.
Yep.
Oh, sorry. If you could see.
That's not connected. You just have to use the.
This one.
Oh, there.
Can you see that?
Yes.
Okay. Perfect.
Yep.
Yeah. So here is where we're looking at the surface dose of the thing, and then it liquefy, and then it quickly goes down like that. So here, this bit here, because that is actually just the glass of the scanner. Here is where we begin to actually look at what the film is. So that bit at the beginning is really only put there so you can kind of see that. But that's where it starts. So, and then why it goes down so quickly is because that's what the film is recorded internally. And I believe that is due to the inaccuracy, if you like. This is a relative dose, but from the absolute, I know that it's quite low. It goes past the accuracy, I believe, of the film, and so it's just not picking it up anymore, I believe.
Okay.
And so that's why you can see a massive difference there. I only put it in really out of interest to explain the result we got there. But yeah, that's why basically. And that 5% accuracy is just where it's crossed over right at the surface.
Okay. Thank you very much.
Yeah, no worries.
Michelle, do you have a question?
Thanks, Tom. Nice presentation. Just a little question about the difference between ion chamber measurement and calculation, like TPS. So you were mentioning that there are some differences. Did you expect differences? And if you did, why? Like what is in the planning system that could cause some uncertainties and makes you think like that there could be some differences? What are the reasons? Yeah, between the ion chamber and...
Oh, okay. So just for the ion chamber case.
Yes.
I mean, the difference was quite small, generally. Obviously, for the case with the shield, there's the HU difference there. And for the case without the shield, I mean, the difference was 0.9%. I guess, I mean, no system's perfect, right? I mean, the ion chamber is going to detect, ambient noise and things like that. The treatment planning system is trying to be perfect. But I mean, it's not Monte Carlo, it's just doing a quick simulation. So, I mean, that's effectively the answer. It's just noise, I guess. Scatter, yeah, really generally speaking, all that kind of thing.
Okay, thank you.
I'll just jump in with one quick more question. So do you expect the shielding factor to change? I assume you've only just done one delivery, so one fraction. Do you expect that to change if you did a whole treatment example, instead of one fraction?
It's interesting to see. I don't think it would necessarily because, you know, it's the same dose again and again. The shield isn't going to change necessarily. But a lot of the other studies that have done were done on people that did use fractionated doses. So I'd like to see it to confirm, but I wouldn't expect it to be a major difference.
Okay, so theirs did change.
Well, no,
They did a whole.
so they took fractionated treatment dose, and then they worked it out at the end. So we're taking an average over it.
Yeah, if I may, for time, just want to quickly ask you, great presentation, by the way, Tom. Just for hypothetical sort of clinical implementation, would you foresee any issues with patient compliance and how that could tie in with workflow changes and how it might change the role of the RTs?
Yeah,
in all this?
I mean, that's a huge question. I mean, in part of it, I didn't include it in the talk, but I actually took a little sample size of men between the ages of 18 to 25 to kind of ask them, hey, how do you feel about the shield? Does it terrify you? You know, and most of them were hesitant and thought that if it was, they believed it was going to, a doctor reassured them that it would alleviate dose, that they would accept it, and then that was in all cases. And most of them preferred this particular one to what is commonly used. So if you look, it's quite far away, but I'll find it. What is often used is a kind of clamshell design, which looks like that. And when a lot of people were showing that particular version, which is what we've got at Charlie's downstairs, a lot of them were like, yeah, if I have to choose between that and the other one, yeah, I'll take that. So it's a very good point you might mention, but from what I've observed, I don't think there'll be too much issue with compliance, but obviously you're always going to get one or two people here and there. Does that answer your question?
Yeah, and just in terms of the workflow itself, do you think it would sort of balloon out treatment time much?
Because of the manufacturing process?
No, the actual on couch and setting up the patient.
Oh, I don't think so. In the real situation, I guess you'd need to make sure you've got styrofoam handy to support it because it's quite heavy, and make sure that the person is aware of all that, and so that that's there to kind of hold it. But I believe if compliance isn't an issue, then yeah, I think it wouldn't be too big a deal actually. Yeah.
Thanks very much. Okay.